But in advanced manufacturing, we encounter the depth problem. Because during complex deposition steps, contaminants from poor ALD, nucleations, or high temperature thermal diffusion can often get driven down and trapped deep inside multi-layer structures. So a surface scan will look perfectly clean, even though the device is failing electrically, while a VPDI CPMS taken from the full thin film would give us information that there is some contamination somewhere in the film, but we would not know if it's at the top of the film or if it's at the bottom of the film next to the substrate or if it's somewhere in the middle because there was some kind of process changes in between. The SIMS solution tackles all these problems by intentionally sacrificing the full wafer mapping to look at a specific location in the wafer, but by digging deeper. So instead of sweeping the whole 300 mm wafer, SIMS drills straight down into the bulk material at one highly specific location. This provides incredibly precise elemental tracking across the buried interfaces, showing you exactly what is hiding beneath the surface. Now, to see how SIMS can profile deep into the bulk material, we need to look at its underlying physics. Because unlike TXRF, which generally bounce X-rays off the surface, SIMS rely on highly energetic sputtering process. We take a primary ion beam, which is typically utilizes cesium or oxygen ions, and use it to physically bombard and sputter the surface of the sample. This high energy bombardment physically destroys the lattice, ejecting what we call secondary ions from the bulk materials. These ejected secondary ions are then collected and flown through a mass spectrometer, which separates them based on their exact mass to charge ratio. However, a raw mass spectrometer signal that just gives you relative intensity is not enough. To get actionable engineering data, that raw signal is quantified and converted into the exact concentration, typically in parts per million to parts per billion. This critical quantification is achieved by calibrating the signal against highly specific metrics-matched reference standard. Because we are feeding these ejected ions directly into the mass spectrometer, the detection capabilities of SIMS is quite broad. The technique is capable of detecting all elements across the periodic table, including their specific isotopes. So from heavy uranium all the way down to hydrogen and its isotope.